Hello, in this video, I'm going to give a quick overview of the key points of bayestrader, the trading architecture I designed for Manifold Technologies, and why I believe it is significantly better than any existing architecture that you can find online. So to get right to it, unlike most approaches, which consider assets independently while most a subset of assets at a time, we chose to model the portfolio, or rather the optimal portfolio, to exist on a manifold instead, which can much better capture the dynamically changing relationships between all assets simultaneously. Of course, it is an exceedingly challenging problem to embed such a complex object, such as the entire stock market, which extends beyond just simple pricing data to news as well as macro events onto a manifold. But say we are able to cleverly use the tools of representation learning to generate at least a somewhat useful embedding, then what you would get is something that looks like the following picture. Here we have our portfolio represented by the number 2 blue ball traveling along some surface. In reality, there exists much more than just one optimal portfolio. In fact, the optimal portfolio would be a submanifold of the manifold on which the portfolio is defined on. And as long as our portfolio is within some neighborhood of that submanifold, then we are already doing very well. Hence, we can interpret this surface as the surface on which our portfolio should stick on in order to remain near optimal. So using this framework for our strategies to express the preferences on where the portfolio should be, we have them return actions, which exist on the same manifold the portfolio is defined on. There are many reasons to do this, the first being that the addition operator between a portfolio and an action would then produce a new portfolio, which can then be consumed by an execution algorithm. The second being that we can easily combine multiple strategies by simply employing a weighted sum over the actions generated from each strategy to get another action, and then adding that action to the current portfolio to produce a new portfolio. Finally, of course, fits very naturally into a reinforcement learning framework in which we are always trying to model the optimal action. And so this forms the basis for architectural design, which is a unification of two master strategies working in unison with each other. Master strategy 1 is a differential geometric ensemble algorithm, which takes as inputs every strategy and returns a final action by performing a weighted sum over the actions returned from all the strategies. Now, for this to be useful, the weights must be dynamically changing, and the algorithm would do this by learning how each of the strategies performed in various historical market conditions, and then judging the current market condition to weight the various strategies. Master strategy 2 is a Bayesian reinforcement learning agent, which is supposed to return the optimal action. Now, from the perspective of the optimal reinforcement learning agent, if it indeed always returned the optimal action, then that strategy would be all we need. Unfortunately, we know all too well that in real life, this is almost never the case, as the learning process might not have been so smooth. Even if the data contained enough information to inform an optimal action, the highly non-convex natures of our loss functions might have caused our gradients to settle on a saddle point or even just vanish or explode altogether, resulting in non-optimal actions in certain scenarios. This is where Master Strategy 1 comes in to act as a smoother for Master Strategy 2 by using the other strategies which may perform better in the current market environment. However, from the perspective of Master Strategy 1, Master Strategy 2 is just one of many strategies, of which we might have 5, 10, 15, or even 20 strategies for different scenarios, thus increasing the likelihood that we will always return reasonable actions so long as Master Strategy 1 is trained properly. And so this diagram here actually depicts this quite well. As a reminder, we have an optimal portfolio traveling along some surface, and it needs to stick to this surface in order to remain near optimal. Over here, however, you see that the green line indicates that very quickly, the surface will drastically change, which can be a result of many unpredictable factors, such as China's ban on crypto. And so this also means that the allocation of our assets on our portfolio must likewise also drastically change in a very short amount of time. However, this first red arrow represents the action generated by the reinforcement learning agent. Clearly, you see that if we follow the direction of the action, then our portfolio would shoot way off the surface, and we would arrive at a portfolio that is far from optimal. Now, the blue arrows represent the actions from all the other strategies. And we see here that one of these strategies has detected this drastic change in surface orientation. And so if master strategy 1 is smart, then it would know to heavily upweight the action of that strategy. And so the second red arrow represents the action returned by the overall algorithm. And you can see that it is much closer to being optimal. The last thing I'll mention in this picture is that the lengths of the arrows indicate an optional confidence each strategy can express in its action if it does return 1, and can be helpful as an additional feature for Master Strategy 1. Now with the diagram out of the way, let's quickly go over the code, some of the code which makes all of this happen, and do a quick comparison with one of the most popular trading frameworks that you can find online. Two of the most important classes are the portfolio class and the action class. As you can see, the portfolio class extends MP.ND array because any mathematical object we represent in computers as an array of numbers. Typically, if you go to any brokerage, they will represent the portfolio as a list of shares of each asset you are invested in, along with a cash variable indicating how much cash you have. Now, although this definition is necessary for inputs into actual trades, it is not ideal as the inputs to the first layer of an embedding algorithm, as you would also need metadata information about the price of each share. Hence, we have this identity encoding where each entry stores the percentage of the portfolio's leverage in that particular asset. We also treat cash in the first dimension as an additional asset. This allows us to properly encode the direction and orientation of the portfolio, but by doing so, we lose important information about the size or length of the portfolio. And so to rectify this, we also store an additional variable called market value, which stores the total market value of the portfolio. This allows us to easily project back into the typical portfolio consisting of shares and cash, while also functioning as inputs to geometric encoding of an embedding algorithm. That's the market value. And now that the portfolio is defined, the action class is very simple. It also extends MP.ND array. And by construction, the sum of the action array must always be 0, and similarly, the sum of the portfolio array must always be 1. This helps maintain the invariant that a portfolio plus an action is another action, and that an action plus an action also yields an action. And so now that we have a portfolio and an action, how does a strategy actually work? So every strategy extends the strategy base class, and we must define this one function called getAction, which takes an current timestamp and returns an action. When strategy is initialized, bayestrader also gives them a reference to the data feeds and portfolio. And so to define a simple moving average crossover strategy, we'd be responsible for setting values in the appropriate indices for the assets that we want to buy. You might notice very quickly that it's quite unintuitive to define such an indicator-based approach, and that is by design. To specify how many shares you want to buy, you have to specify a percentage of the portfolio's total allocation into that asset. That by itself is not so challenging, but portfolio and action both maintain invariances. And so if you want to specify that you want to allocate 1% of your portfolio to Apple, then you would also have to specify exactly where to take that 1% out of. This makes the design of dynamic strategies that return actions, such as reinforcement learning agent, very intuitive to design, and forces the strategy designer to consider the relationships between all assets simultaneously, and to think about the manifold in which the portfolio is defined. Now, as a side note, to facilitate the development of such indicator-based approaches, since they are the norm, we've designed these helper functions on action called buy and sell, which represent the notion of having a strategy express a preference to buy or sell an asset. And this just simply moves percentage allocations from the asset specified in and out of the cash index, which we also consider as another asset. And so putting all of this together, in bayestrader, all the communication is managed by a central class called Cerebral. And the main need for such a class is because the architecture is synchronous and not concurrent. And so this is achieved by discretization of the trading day into blocks, of which I chose to define as 5 minutes, since our data is on the scale of minutes. Regardless, we see that the produce function over here is part of the next execution block function. And the produce function computes a weighted sum over all the actions returned from each of the strategies and adds it to the current portfolio to get a new portfolio, which is then consumed by an execution algorithm. There are also many other components required here to make the system running, such as the data feeds, the actual execution algorithm, a broker when we're trading live, and this connects to interactive brokers, a broker simulator for backtesting purposes, And not to mention the entire ingestion pipeline filled with many algorithms defined in these helper files here that clean, parse, and pre-process our data and insert it as well into our database, which manages connections from our different data feeds and also stores our data. There's also glue, such as helper functions over here, global variables, and some types, observers, loggers, so scripts to control how bayestrader runs, as well as the interactive brokers trader workstations. And we must simulate that on virtual screen and use a separate program to help us log in, since we cannot click the login buttons of a Java application on an Amazon Web AWS server. But I'll go over all of this in a separate, more in-depth video. So the last thing I wanted to talk about is to do a quick comparison between bayestrader and one of the most popular frameworks online that you'll find is called backtrader. The names are quite similar. So when I first designed bayestrader, I actually took a lot of inspiration from the core design approaches taken by backtrader, because back then I just wasn't nearly as proficient or confident in my coding abilities to design an entire architecture mostly by myself, like I am now. And so we borrowed some of their ideas, the main one being a central class called Cerebral to manage all the communications. Getting right to the point now, base is backtrader's strategy definition. We see that there is no abstraction from strategy definition to order execution. You simply execute orders based on static if conditions, specifying how many shares you want to buy and a certain condition is met. There's also a big deal made about indicators, which compute a pre-specified function on recent historical data. And this makes it very intuitive to design indicator-based approaches, such as a moving average crossover, since, as I said, all you need to do is specify a static condition and specify how many shares you want to buy. But how do you even start to define a strategy that is supposed to return an action, such as a reinforcement learning agent that expresses its preference over all the assets simultaneously by looking at the portfolio embedding? You could do it here by storing the portfolio embedding inside the strategy init somewhere, compute the action separately at every timestamp here next, and then project it back to orders and execute them here. But this wouldn't be very intuitive since you were trying to do something the framework was not designed for. Not to mention, this framework also doesn't scale since you have to load input data every time separately for each ticker. And they're all from flat files as well. And the framework even tells you in its documentation that it's not fast to backtest multiple stocks at the same time, thus reinforcing the notion that assets be considered independently, or at most a small subset at a time. There's also no execution algorithm, so strategists have to worry about everything from portfolio embeddings to action generation and summing to very slow queries of data when you load in multiple stocks at a time, as well as actual order execution, whereas bayestrader separates each of these very important pieces into its own component and scales with efficient complexities and constants. This framework is really only meant to be used for researching purposes, but even for those purposes, its design is too unintuitive for me to justify using, except to gain some inspiration for the many very useful metrics that they offer in system design components. But by now, we pretty much have all of those already. And that's basically a wrap on this overview. If you're interested in a more in-depth video where I go over the additional components to make bayestrader run, such as the ingestion pipeline, database, and the glue to hold everything together, I'll link another video below where I go over those details and a lot of the design decisions that had to be made.